In part 4 of this talk, I am going to describe some exotic lightning phenomena that can happen on Earth. Let's start from this slide where you can see a very schematic view of the Earth's surface and the atmosphere layers, which are the troposphere, the stratosphere, the mesosphere, the ionosphere, and the thermosphere. These extend out to the outer space. Typical lightning strikes, the ones that we see during thunderstorms, occur in the troposphere and they hit the Earth's surface. But actually there are also many other kinds of exotic lightning phenomena that can happen on the Earth, and today I'm going to describe two of them, the St. Elmos fires and the volcanic lightning. Moreover, when we move up into the atmosphere, we can see that other kinds of exotic lightning phenomena, like blue jets, sprites, and elves, can also occur. Today, I'm going to give you a description of them as well. Moreover, since this is CoffeeShop Astrophysics, I will also spend a few words and show you a few images of lightning that has been observed on other planets. Let's start from St. Elmos fires. This curious name comes from Saint Erasmus of Formia, who is the patron saint of sailors. In fact, this phenomenon was usually observed by sailors during thunderstorms on their ships. As you can see from the old painting on the left, sailors would actually see blue-violet light coming out of the sharpest points on the ship itself. In the center, you can see a real image of some St. Elmos fires happening on a transmission line. But how are these phenomena produced? Well, the sharp points actually accumulate charges. And as a consequence of that, a large charge difference is produced between the sharp points themselves and the air. And as a consequence of this, the atoms in the air are torn up. In this small figure here, I am showing you a schematic view of the basic structure of an atom. I also want to remind you that atoms form everything that surrounds us, including the air. Atoms are formed by a central nucleus surrounded by electrons. Electrons are here represented as yellow particles. Electrons are negative charges, and for the sake of simplicity, here they are represented as spinning around the nucleus on circular orbits. So, under the effect of the large charge difference between the sharp points and the air, the atoms in the air start losing electrons. So, for a while, we have basically free electrons which move into the air. But after some time, these electrons will reunite with the nuclei and will reassemble into atoms. And when this recombination occurs, that's when the blue-violet light of the St. Elmos fire is emitted. The atoms which are mainly responsible for the blue light that we see are nitrogen atoms. In fact, nitrogen is very abundant in the troposphere. Moreover, St. Elmos fire can also be accompanied by a cracking or a hissing noise. Another exotic lightning phenomenon that can happen on Earth is the volcanic lightning. The first event of this sort was reported in 79 AD when Mount Vesuvius in Italy erupted. On the left, you can see the eruption of the Taal volcano in the Philippines in January 2020. So this is a pretty recent event. And you can see in this figure that the volcano is actually the little mountain in the pink circle. You can so realize how big the ash plume produced by the eruption is. Moreover, you can here see also a very strong lightning strike happening. We know that the main ingredient that we need in order to produce a lightning strike is, in the case of normal thunderstorms, ice particles that rub against each other and gain charge. But what kind of particles can actually do that in the ash plume of a volcano? Well, these particles can actually be ash particles in the plume, or again, ice particles. It is in fact amazing how much ice we can actually find in the ash plume of a volcano. This ice comes from the evaporation of water that can be close to the volcano, like in the sea or in a lake, by means of the hot magma which is produced during the eruption. So this water vapor starts traveling into the plume and it's brought up to the upper layers of the atmosphere, where the temperature is very, very low. So what happens is that this water vapor is turned into water and then into ice particles. And that's where the ice particles we need to produce a lightning strike come from. The lightning strikes produced in this case are very similar to just typical lightning strikes, so they are followed by thunders as well.